Okay, we're picking up with part 2 of 5.3. We're talking about identifying zeros and their multiplicities. So we've talked about zeros but not multiplicities before. So let's talk about what that is. If a polynomial contains a factor of the form x minus h to the p, the behavior near the x-intercept h, okay, so remember when we have a polynomial factored and we set it equal to 0, we can set each factor equal to 0 to find the zeros, and the zeros would be right here. So if it was x minus 2, then the 0 would be 2. So going back, let me just start over. If a polynomial contains a factor of the form x minus h to the p, the behavior near the x-intercept h is determined by the power p. So again, if this was x minus 2, whatever this exponent is would determine the behavior near that x-intercept. So we say that x minus h is a 0 of multiplicity p. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. So if this was squared, if it was cubed, if it was not cubed, I'm sorry, squared to the fourth, anything like that, those multiplicities, if it was even, the graph will just touch that x-intercept and kind of bounce off. So the graph will cross the x-axis at zeros with odd multiplicities. And then if you add all the multiplicities, the sum is the degree of the polynomial function. So if you add all the multiplicities, you get the degree of the function without having to multiply it out. So that'll save you some time. So let's look at these. Given a graph of a polynomial function of degree n, identify the zeros and their multiplicities. So again, let's look at what happens. If the graph crosses the x-axis and appears almost linear at the intercept, it is a single zero. Okay, so now it appears almost linear. It doesn't mean that it is linear, but the point is that it looks almost linear and it's crossing the x-axis. That would be a single zero. So a single factor would represent that. So then here, if a graph touches the x-axis and bounces off the x-axis like it's doing here, see how it touches and then bounces off? It is a 0 with an even multiplicity. So the exponent here would be 2 or 3. I'm sorry, I said that wrong. Would be 2 or 4 or 6, so an even multiplicity. Now, notice this one doesn't bounce off. It crosses just like this one does, but when the graph crosses the x-axis at a 0, it is a 0 with an odd multiplicity. So if it crosses like it did here or here, then that would be an odd multiplicity. Now it doesn't say it, but the flatter this gets, the higher the multiplicity is. Okay, so this would be a single multiplicity. This is a multiplicity of at least 3 because it looks almost flat here. So if it's almost flat, then and it crosses the x-axis, it means it's odd. So it can't be 1. This would be a multiplicity of 1, a single. This is almost flat where it crosses, so flat as in almost horizontal. So you would say that that is 3 or above, and it has to be odd because it crosses. All right, so use the graph of the function of degree 5 to identify the zeros of the function and their possible multiplicities. So this is degree 5, so I know all the degrees add up to be 5. So there are the zeros. I have a 0 at -3. I have a 0 at -2. And I have a 0 at 1. Okay, so let's just look at the behavior at each one. So this one crosses, so this will be odd, and it's almost linear. So I would say that is a multiplicity of 1. this is almost linear, so this is a multiplicity of 1. And then look at this one. It crosses, so that means it's an odd multiplicity. It's odd, but it's almost, it's not almost the straight line here. It's flat, almost flat right there. So this is a multiplicity that is odd, but it's bigger than 1. So I would say it's going to be a multiplicity of 3 or more. Now let's add up these multiplicities. 3 plus 1 plus 1, and we get 5, which is what it should add up to be. So just for kind of where we're going, a possibility for this would be x plus 3 would give us the 0 of x minus 3. X plus 2 would give a 0 of negative 2. And x minus 1 would give a 0 of 1. And this is to the first power, this is to the first power, this is probably to the third power. So this would be kind of how you could try to figure out what an equation would be. Now I'm not exactly sure if there would be an a involved here, but other than 1, but it kind of gives you a starting point to go with. Okay, so your turn to try it. Identify the multiplicities. Use the graph of the function of degree 9. So the degree is 9, so that might help you to figure in the figure to identify the zeros of the function and their multiplicities. So pause the video, come back, and then we'll go over it. All right, so we have a 0 at negative 5. And it's almost flat, so I would say the multiplicity, it has to be odd, so I would say at least 3. So we'll start with 3. Now, there's another one here at negative 1, and that bounces off, which means it's even. So this one was odd. This one we know is even. So we'll say a multiplicity of, we'll start with 2, see if that works. All right, now look at this one. This one bounces off at 3. So if it bounces off, it's an even multiplicity. But do you see how it's flatter here, almost horizontal, than this one was? This one kind of bounced back off, but this one kind of flattens out before it bounces. So the flatter it gets, the bigger the multiplicity. So I'm going to go with a multiplicity of bigger than 2, and I'm going to skip to 4. And the reason I chose 4 is because it had to be even. So if it was bigger than 2, the next bigger would be 4. So if we add these together, 3 plus 2 plus 4, we get a multiplicity, a degree of 9. Okay, so again, the flatter it gets, the bigger the multiplicity. If it goes through the 0, it's odd. If it bounces off the 0, it's even. And this slide here is just a review of end behaviors that we learned in 5.2. So just remember, if A is positive, the leading coefficient, if the leading coefficient is positive, then the right behavior points up. If A is negative, the leading coefficient is negative, the right behavior points down. So that means that as it's approaching positive infinity on the x, if A is greater than 0, if A is positive, then f of x is also approaching infinity, if for even degrees. But also, that's the same as for odd degrees as well. As x approaches infinity, f of x approaches infinity. As x approaches infinity for a negative leading coefficient, f of x approaches negative infinity. Same thing for the odd. Then the left behavior is determined by the even or odd degree. So if the A determines the right behavior, the left behavior is determined by whether the degree is even or odd. And so what that means is if it's even, the end behaviors point in the same direction. So if it's even, if the right approached positive infinity, then the left will also approach positive infinity. If it's odd, they approach different directions. So this little slide here should help you. And again, that was a review. Also a review of turning point. You can kind of see that there. A turning point is the point in the graph where the graph changes from increasing to decreasing, or vice versa. So a polynomial of degree n will have at most n minus 1 turning points. So that was a review from the last section as well. So find the maximum number of turning points. So the highest degree here is 5x to the 5th. So 5 is the highest degree. So in this case, the number of turning points would be 1 less than that. So it would be 4. For this next one, what you can do is to find the degree is to add the multiplicities. So here's a multiplicity of 2, that's 2, so 2 and 2 would be a degree of 4. So the number of turning points is 4 minus 1, which is 3. So rather than having to multiply it out to find the degree, you can just add up the exponents to find the degree. All right, so now let's talk about sketching the graph. So the first thing you're going to do is find the intercepts. If you're given a polynomial function, find the intercepts first, and then you can plot those. Check for symmetry. If the function is an even function, its graph is symmetric about the y-axis. So remember, you put in negative x and see if you get f of x. If a function is an odd function, its graph is symmetrical about the origin. So if you put in negative x, you get the same as negative f of x. Use the multiplicities of zeros to determine the behavior at the x-intercept. So if it's odd, it goes straight through. If it's even, it bounces. And if it's a larger multiplicity, then it's going to kind of flatten out at that place. Then determine the end behaviors by examining the leading term, and use the end behaviors and the behavior of the intercepts to sketch the graph. And then ensure that the number of turning points does not exceed 1 less than the degree of the polynomial, and then we can use technology to check our graph. So it seems like a lot going on, but it's actually, I think, a little bit easier than it sounds. So the first thing that I would do is I would find the y-intercept and the x-intercept. So to find the y-intercept, I'm going to set x equal to 0. So negative 0 plus 1 squared times 0 minus 4. So that's negative 1 squared times negative 4. So 1 squared is 1, but the negative is not inside of that parentheses. So it would stay negative 1 times negative 4, and I'm going to get positive 4. So that's the point 0, 4. So I'm going to go ahead and plot that. All right. So now let's find the x-intercepts. We're going to set the f of x equal to 0. And what's nice about this is it's already factored out for us. So we can just set x plus 1 squared equal to 0 and x minus 4 equal to 0. So here we square root it and we get x plus 1 equals 0. So x equals negative 1. And here we add 4 to both sides and we get positive 4. So negative 1 and positive 1, 2, 3, 4. So now we need to find the multiplicities. So the multiplicity here is 2. So that's even. So that means it's going to bounce. So at x equals negative 1, it's going to bounce. It's going to bounce off the x-axis. The the multiplicity here is 1. It's single, so it's going to go straight through. So the question is, does it go straight through this way or does it go straight through that way? So let's look at some end behaviors here. So end behaviors, let's see, if okay, check this out, it's negative. This is negative. And then we already said that the degree is, we didn't actually say 2 plus 1 would be 3. Degree is 3. So that means that the negative here tells us that the end behavior is pointing down on the right. And because it's degree 3, the left behavior is going to go in the opposite direction. So it's going to be pointing up like this. So I'm guessing the straight through means that this is going to go through here this way, which means this is going to go something like that. Actually, it probably goes up like that and then comes back down. Now, is this graph exactly accurate? No, we're just sketching it. We're just sketching the shape of the graph, but we can definitely check Desmos to see what it should look like to see if we're close. So we had negative parentheses x plus 1 plus 1 squared times x, I believe it was minus 4. And if you look, that's kind of what we did. It bounced off at negative 1 and went straight through at 4. And then if you will recall, look at what we drew here. You can kind of compare the two. So we did get the basic shape there. Okay, so let's look at this. Try it. F of x equals 1/4 x minus 1 to the 4th times x plus 3 to the 3rd. So find the zeros, find the y-intercepts, find the multiplicities, figure out that behavior, figure out the end behaviors, and see if you can sketch the graph. And when you're finished, come back and we will check it. Okay, let's look at this one. So first we want to find our intercepts. So we're going to find our y-intercept. So we're going to do that by setting x equal to 0. So f at 0 is 1/4 times 0 minus 1 to the 4th times 0 plus 3 to the 3rd. So 1/4 times 0 minus 1 is negative 1. Negative 1 to the 4th is positive 1. 3 to the 3rd, 0 plus 3 is 3. 3 to the 3rd is 27. So we get 27/4, which is 6.75. So I have the point 0, 6.75 as the y-intercept. So I'm going to go ahead and plot that. 0 up 1, 2, 3, 4, 5, 6.75. So somewhere in there. So now to find the x-intercepts, we just take each factor and set them equal to 0. And so if we added 1 to both sides, we get 1. We add negative 3 to both sides, we get negative 3. So we have the points 1, 0, and 0, negative 3. So 1, 0, and 0. Oops, I wrote that wrong. It should be negative 3, 0. I apologize. Okay. So I know 3 points on the graph. Now I need to figure out some behaviors. So let's look at A. A is 1/4, which is positive. So that means that the right behavior is going to go up. So I know this side is going to go up. Let me do a different color. And then the degree is 4 plus 3, which would be 7. So because that's odd, the left behavior would be opposite. So the behaviors are going to look like left and right. The left is pointing down, the right is pointing up. So as x is approaching negative infinity, f of x approaches negative infinity. As x approaches infinity, f of x approaches negative infinity. Now let's check out the multiplicities. The multiplicity of this first one, it was to the 4th power, so multiplicity of 4. The second one was to the 3rd power, so that's a multiplicity of 3. So this is even, so it's going to bounce off. But it's big, it's a large multiplicity. It's going to kind of flatten out first. And then this one is odd, so it's going to go straight through, but 3 is larger than 1, so it's going to flatten out as well, kind of flatten out like that. All right, so let's kind of put this all together. I'm going to connect those. Going to connect this. Now, what's going on here is I think it's going to go up and then come back down, something like that. So your graph more or less looks something like this. I'm not sure how high it goes, but that's the basic gist. Again, it looks like it's flattening here and flattening here because of the large multiplicities. So the other thing we want to look at is the number of turning points. With degree 7, we can have at most 1 less than that, at most 6 turning points. And as long as we don't have over 6 turning points, we're good. So it looks like we have a turning point here where it changes direction, and a turning point here where it changes direction. So it's not 6, but that was the maximum number that you could have. So as long as it's not over 6, we're good. All right. So we're going to stop here, and we will pick up with the next slide in part 3.